Hello students, today's topic is acid and bases, an overview of different concepts. Our recognition of some chemical substances is acid and certain others is bases rests on some experimental facts about these substances. Acid and bases possess some opposite properties. Acid turn blue litmus red and the bases turn red litmus blue. Acid counter the effect of bases and vice versa, the process being called neutralization. Some acid liberate hydrogen when reacting with some metal ions. There are several so-called theories of acid and bases. Which is most useful theory or definition of acid and bases? The answer depends on whether we are considering ionic reaction in aqueous solution, in non-aqueous solution, or in a fused melt, and whether we require a measure of the strength of acid and bases. For this reason, we need to be familiar the following four theories. Number 1, Arrhenius theory or water system theory. Number 2, Bronsted-Lowry theory or protonic theory. Number 3, Lewis theory or electronic theory. And number 4, Lux-Flood definition. Acid and bases different theories. Number 1, Arrhenius theory. In 1884, Arrhenius suggested the theory of electrolytic dissociation and proposed the self-ionization of water. Water ionized is hydrogen ion and hydroxide ion. According to Arrhenius, substances producing hydrogen ion or hydronium ion are called acids, and the substances producing hydroxide ion are called bases. Thus, HCl is an acid and the NaOH is a base. HCl acid reacts with NaOH base to give NaCl salt and water, or simply hydrogen ion combines with hydroxide ion to give water. Hence, water acts as an acid and base. Limitation: it recognizes dissociation and the acid-base reaction in aqueous medium only and not in non-aqueous solvent and the aqueous form. HCl is regarded as an acid only when dissolved in water and not in some other solvent such as benzene or when it exists in the gaseous form. Roman 2.2, it cannot account for the acidic and the basic character of the materials in non-aqueous solvent. For example, ammonium nitrate in liquid ammonia acts as an acid, although it doesn't give hydrogen ion. Number 2, Bronsted-Lowry theory. According to this theory, a substance, a molecule or a cation or an anion which can split up a proton is called an acid, while a base is a substance which can take up a proton. In short, an acid is a proton donor and a base is a proton acceptor. For aqueous solution, the Bronsted-Lowry definition doesn't differ appreciably from Arrhenius definition of hydrogen ion, that is acid, and the hydroxide ion, that is bases. Water, pure solvent, hydrogen ionized ion acid, and the hydroxide ion base. This theory makes acid-base reaction independent of solvent as follows. HCl acid reacts with NH3 base to give chloride ion and ammonium ion. Ammonium ion acid reacts with hydroxide ion base to give ammonia and water. Conjugate acid base here. Let us consider a reaction. HCl strong acid 1 reacts with water strong base 2 to give hydronium ion weak acid 2 and chloride ion weak base 1. Here hydrochloric acid donates a proton to water and is therefore an acid. Water on the other hand accepts a proton from HCl and is therefore a base. In the reverse reaction, the hydronium ion donates a proton to chloride ion. Hence, hydronium ion is an acid, chloride ion is a base because it accepts a proton from hydronium ion. Thus, strong acid 1 HCl and the weak base 1 chloride ion form one conjugate acid base pair, and the weak acid 2 hydronium ion and the strong base 2 water form another acid base pair. It follows that the stronger acid and the weaker base form one conjugate acid base pair, and the weaker acid and the stronger base form another conjugate acid base pair. Limitation. Point number 1. This theory cannot be used to explain the creation occurring in non-protonic solvents such as SO2, AlCl3, COCl2, SOCl2, etc. Number 3, Lewis theory or electronic theory. According to G.N. Lewis, an acid is any species, molecule, radical or ion that can accept an electron pair to form a coordinate covalent bond, and a base is any species that can donate an electron pair to the formation of a coordinate covalent bond. Thus, an acid is an electron pair acceptor and a base is an electron pair donor. A typical example is hydrogen ion proton. Acid reacts with ammonia base to give ammonium ion. In this reaction, proton accept one electron pair from ammonia molecule and is therefore an acid, whereas ammonia molecule which donate an electron pair is a base. Limitation: it is not possible to arrange string of Lewis acids and bases in any order of their relative strength, since they are found to depend on their type of reaction. Classification of Lewis acid and bases into hard and soft acid and bases. R.G. Pearson has classified the Lewis acids and the Lewis bases as hard and soft acids and bases. The third category, whose characteristics are intermediate between those of hard and soft acid or bases, are called borderline acids and borderline bases. Soft and hard bases. Soft Lewis bases are those in which the donor atom are easily polarized and have low electronegativity. Hard Lewis bases are those in which the donor atom have low polarizability and high electronegativity. Table 1 contains some typical bases which are classified as hard, borderline and soft bases. Table 1, classification of bases. Hard bases: H2O, OH minus, F minus, CH3, COH minus, PO3 minus, SO4 2 minus, Cl minus, CO3 2 minus, ClO4 minus, NO3 minus, ROS, RO, R2O, NH3, RNH2, N2H4, where R is alkyl or aryl group. Borderline bases: C6H5NH2, 66H5N, N3 minus, Br minus, NO2 minus, SO3 2 minus, N2. Soft bases: R2S, RSS, RS minus, I minus, SCN minus, H2O3 2 minus, R3P, R3AS, Cn minus, RCN, CO, C2H4, C6H6, hydrogen ion. Soft and hard acid. Methyl complexes with different donor atom can be classified into two sets based on the sequence of their stabilities: class A acid or acid, hard acid; class B acid or soft acid. Lewis acid can now be classified into three categories: hard, borderline and soft acid, as shown in table 2. Table 2, classification of Lewis acid. Hard acid: H plus, Li plus, Na plus, K plus, Be2 plus, Mg2 plus, Ca2 plus, Sr2 plus, Mn2 plus, Al3 plus, Ac3 plus, Ga3 plus, In3 plus, La3 plus, Lu3 plus, CO3 plus, Fe3 plus, As3 plus, Si4 plus, Bf3, LCl3, SO3, Cr6 plus. Borderline acid: Fe2 plus, CO2 plus, Ni2 plus, Cu2 plus, Zn2 plus, Pb2 plus, Sn2 plus, Sp3 plus, Bi3 plus, RH3 plus, SO2, NO plus. Soft acid: Cu plus, Ag plus, Au plus, Tl plus, Ig plus, Pd2 plus, Cd2 plus, Pt2 plus, Ig2 plus, Tl3 plus, BH3, I plus, Br plus, I2, Br2. Zero valent methyl atoms. Soft acid form stable complexes with bases that are highly polarizable, are good reducing agent and not necessarily good bases towards the proton. Hard acid, on the other hand, usually form stable complexes with bases that bind well with proton. Soft and hard acid and bases have principle and the stability of complex AV. The typical Lewis acid base reaction can be generalized as follows: A Lewis acid reacts with B Lewis base to give AB complex. The concept known as half principle is very helpful in making a prediction of the stability of the complex AB. This principle was proposed by Ralph G. Pearson. According to this principle, the complex AB is most stable when A and B are either both soft or both hard. The complex is least stable when one of the reactant, namely A and B, is very hard and the other one is very soft. This principle states that hard acid prefer to bind hard bases and the soft acid prefer to bind soft bases, and thus a more stable product will be obtained. Number 4, Lux-Fluid definition. This acid-base definition was a revival of oxygen theory of acids and bases proposed by German chemist Hermann Lux in 1939, further improved by Hakon Flood circa in 1947, and still used in modern chemistry, geochemistry and the electrochemistry of molten salts. This definition describes an acid is an oxide ion acceptor and a base an oxide ion donor. A typical example is calcium oxide base reacts with silicon dioxide acid to give calcium silicate. The Lux Plus base is a basic anhydride. Calcium ion reacts with oxide ion and the water to give calcium ion and the hydroxide ion. And the Lux Plus acid is an acid anhydride. Silicon dioxide reacts with water to give hydrogen silicate. This system is useful in dealing with anhydrous reaction, melt of oxide and the other high temperature reactions such as are found in metallurgy and the ceramics. Comparison between acid and bases as defined by Arrhenius, Bronsted-Lowry and Lewis. Roman 1. Arrhenius acid is a compound that gives hydrogen ion or hydronium ion in water, and the Arrhenius base is a compound that furnishes hydroxide ion in water. Roman 2. Bronsted acid is a proton donor and the Bronsted base is a proton acceptor. Roman 3. Lewis acid is an electron pair acceptor and the Lewis base is an electron pair donor. Roman 4. Arrhenius acid and the Lewis acid are the same substances. That is, the substances that act as Arrhenius acid also act as Lewis acid. Conclusion. Arrhenius theory cannot account for the acidic and the basic character in the case of non-aqueous solvent. According to Bronsted-Lowry, an acid is a proton donor and a base is a proton acceptor. A conjugate base of an acid is that part left after the proton is lost, while the conjugate acid of a base is the species formed on the addition of a proton to the base. Thus, stronger acid and the weaker base form one conjugate acid base pair, and weaker acid and the stronger base form another conjugate acid base pair. Furthermore, proton transfer reaction leads to the formation of the weaker acid and the weaker base. An acid, according to Lewis, is an electron pair acceptor and a base is an electron pair donor. Arrhenius acid is and Lewis acid are the same substances. Thank you.
Tremendous.